Section 10.4 is concerned with the topic of phase diagrams. Phase diagrams describe how the phase of a sample of matter varies with pressure and temperature. So we have seen that the factors which determine the state of a substance include the strength of the intermolecular forces between particles, the pressure of the system, and the temperature of the system. A phase diagram is a way of indicating how pressure and temperature affect the physical state of a substance. A typical phase diagram will have pressure on the y-axis and temperature on the x-axis. And then it'll have labeled the various phases that are present over the range of the phase diagram. And it'll have a series of lines that separate the different phases. So here we can see a green line, a blue line, and a red line. You'll see where the lines meet, there are a couple of points that are labeled with specific names. In particular, the triple point and the critical point. So, what do all these lines mean? What are these special points? And how do we read the phase diagram? The first thing that we want to note is that if we increase the pressure on a sample of matter, we're going to make it a little bit more dense. Yeah? And if we increase the temperature of a sample of matter, we're going to make the particles move more. So let's have a look at this and think about what this means that if we have a fixed pressure and we increase the temperature. So let's just look at the line that's at 1 atm, this dotted line here, and see what happens as we increase the temperature. So as we increase the temperature, we go from solid to liquid to gas. So what we're really saying is that as we, at a constant pressure, as we increase the temperature, everything moves around more and separates from each other and becomes less dense. So warming our sample of matter up gives the particles enough energy to overcome the intermolecular forces that are holding them together. So we'll start kind of working sort of left to right, understanding what these different lines are. So this green line here that I've got sort of like enclosed within a rectangle represents temperature and pressure points at which sublimation, a solid becoming a gas, and deposition, a gas becoming a solid, occurs. So this green line separates the solid from the gas. Now, if we think about picking a particular temperature, so we'll kind of have the same amount of energy in the system, and we increase the pressure, we end up in the more dense phase, which is not surprising because we're just pushing the particles closer together, right? So this line makes sense that it has the positive slope that it does. Okay, so when we follow the green line to its end, and we end up at this point here where the three lines intersect, and that's described as the triple point. And the triple point is a fun point because it's where all three phases are in equilibrium. So what that means is you have simultaneous melting or freezing and boiling occurring. So everything's happening all at once, and we have solid, liquid, and gas present in equilibrium, which is kind of fun. Something to note about the triple point is if you're at a pressure lower than the triple point, then there's no liquid phase. You can see on the diagram that the liquid phase doesn't come into existence until we are above the pressure of the triple point. Now, for liquid water, the triple point is much less than 1 atmosphere, so we do observe liquid water at atmospheric pressure. However, if we go to something like CO2, where the triple point is well above 1 atmosphere. And that's why we don't see liquid CO2 at normal atmospheric pressure. At normal atmospheric pressure, only solid and gaseous CO2 can exist. So for this reason, carbon dioxide is often referred to as dry ice because at atmospheric pressure it can never be a liquid. And this is helpful for us because we can pack perishable goods in dry ice, and knowing that it'll never form a liquid, that means that those goods will stay cold, but they won't ever get soggy because the solid dry ice will just turn into gaseous dry ice and keep everything nice and dry. Now, the next line that we'll look at is the line that separates the solid and the liquid. And for water, this line leans to the left. This line represents the temperature and pressure points where melting and freezing occur. And yeah, so are there any consequences for this line leaning to the left? Well, let's think about this. Let's pick a particular temperature in the solid area, and then we're going to raise the pressure. That line was meant to be vertical, but I'm not a great artist. And what happens when we raise the pressure? We end up in the more dense phase, which for water is the liquid, because we know that ice is less dense than liquid water. So this diagram is confirming that liquid water is more dense than solid water for H2O. And this is unusual. Water is unusual in that the liquid phase is more dense than the solid. More typical would be the phase diagram for CO2, where you can see that the line separating the solid from the liquid, it leans to the right. So if we pick a particular temperature and we raise the pressure, we end up in the more dense phase, of course, because we're squashing everything closer together, and we end up in the solid. And again, this is more typical in that solids tend to be more dense than liquids. So most of the time, that line is going to be leaning towards the right rather than leaning towards the left. Okay, so our next line over is this red line that I put in the rectangle here. And the red line separates the liquid from the gas. So this red line represents temperature and pressure points where we're having boiling and condensation occurring. And again, if you pick a particular temperature point and you raise the pressure vertically, as expected, you end up in the more dense phase, and this is telling us that liquids are more dense than gases. So there's something interesting about this line. So it's got a positive slope almost always for all substances. I don't know any that have a negative slope. But what it's really telling us, you can see here, is that as the pressure goes up, the boiling point goes up because of its slope, right? So you see that as the pressure goes up, the boiling point goes up. So this is kind of cool because if we go to the mid-ocean ridges where there's a lot of volcanic activity at the bottom of the ocean floor, even though the temperature is really high there, because we've got basically like volcanoes down there, and because the pressure is really high, the ocean doesn't actually boil. So that's kind of cool, right? So it's an interesting manifestation of this phenomena. Of course, the opposite is true. As you decrease the pressure, the boiling point goes down, and this has some interesting consequences for people that live at altitude. So if you're cooking a meal at 15,000 feet, then the boiling point of water is only 87 degrees Celsius. So it's like your food's going to kind of taste not quite hot. This can actually have consequences for people because every 10 degrees Celsius fall in temperature, we typically see a halving in the rate of chemical reactions. So people that live at altitude, often they have to lengthen the time that they cook things for, especially with baking, where baking is often dependent on like the rising of or the reaction of fermentation reactions to cause the rising of breads and cakes and things like that. And you may even have seen instructions on food where it gives advice to extend the cooking time if you live above 10,000 feet, which is kind of interesting. Okay, so we have one last point that it would be nice to look at, which is this point at the end of the line that separates liquid from gases, that's labeled as the critical point. So it's important to realize that as we increase pressure, gases become more dense, and as we increase temperature, liquids become less dense. So eventually you get to a point where you have what's called a critical point, where the density of gases and liquids are equal. So beyond this point, we enter into what's called the supercritical region. And what we have is we no longer have a liquid and a gas in equilibrium, but we have a supercritical fluid that has a density that's sort of in between that of liquids and gases, but a viscosity of gases where there's a tendency for the substance to fill its entire container. So beyond the critical point, we have a supercritical fluid. So supercritical fluids have densities similar to liquids, but viscosities similar to gases. That is, they're fairly dense, but they tend to fill their container. So they're this sort of like hybrid, if you will, in terms of their properties of between a liquid and a gas. And they're really quite cool. So in particular, supercritical CO2 is commonly used in industry because it's non-polar, CO2 is non-polar, to extract oils and other substances from plants and foodstuffs. And perhaps the most common application of this is decaffeinating coffee. So CO2 is nice because it's pretty non-toxic. So using it in the food industry or the pharmaceutical industry, it's a great alternative to other non-polar solvents that are often quite toxic. Okay, so that concludes the video for section 10.4, which is concerned with phase diagrams.